Hello everyone, welcome back to another lesson in our Digital Systems video series. In the previous lessons, we learned how truth tables are constructed and how logical expressions can be analyzed step by step. Now it's time to practice. In this lesson, we're going to solve truth table exercises together using a simple and systematic approach. As the exercises progress, we'll gradually work with more complex logical expressions. So let's get started. Now that we understand how truth tables are constructed, let's start practicing with some guided exercises. In each example, we'll follow the same step-by-step process used in the previous lessons. First, we identify the number of input variables, then we determine the number of rows required for the truth table. After that, we complete the input combinations, and finally, determine the output value of the logical function. And remember, in this lesson, it's extremely important that you pause the video and try to solve each exercise by yourself before checking the final result. So let's begin with our first exercise. Pause the video and try to solve this exercise by yourself before checking the final result. Alright, if you already tried it, let's solve it together. Notice that this logical function contains a NOT operation. And the purpose of the NOT gate is to invert the logical level present at the input. In other words, when the input is equal to 0, the output becomes 1. And when the input is equal to 1, the output becomes 0. In this Boolean expression, we have one input variable. Therefore, our truth table must contain two rows, two input combinations. Since there's only one input column, the input can have only two possible logic values, 0 and 1. So to complete the output column, we simply analyze the value of A in each row and write its opposite logic value. For the first row, A is equal to 0. Therefore, the output becomes 1. For the second row, A is equal to 1. Therefore, the output becomes 0. As we can see, the output column represents the inverted version of the input column. Let's move on to our second exercise. This time, we have a logical OR operation with two input variables. As we can see, the logical expression is A plus B. And below, we have its equivalent logic circuit implemented with an OR gate, okay? Now, it's your turn. Pause the video and try to solve this exercise by yourself. Alright, if you already tried it, let's solve it together. As always, the first step is to identify the number of input variables. In this expression, we have two inputs, A and B. Therefore, our truth table must contain four input combinations, 4 rows, okay? Now let's complete the first input column. Since A is the most significant bit, its values change every 2 rows because it has a weight 2 to the power of 1, which gives us 2, okay? Therefore, we obtain 0, 0, 1, 1. Next, we complete the second input column. Since B is the least significant bit, its values alternate every row. Therefore, we obtain 0, 1, 0, 1. Now we can determine the output values of the logical expression. Remember that an OR gate produces a logic 1 whenever at least one of its inputs is equal to 1. The output becomes 0 only when all inputs are equal to 0. Now, let's analyze each row, okay? For the row 0, we have A equals 0 and B equals 0. So the combination 0 or 0 results in an output 0. For the row 1, we have A equals 0 and B equals 1. So the combination 0 or 1 results in an output 1. For the row 2, we have A equals 1 and B equals 0. Therefore, the output becomes 1. And finally, row 3, we have the combination 1 or 1, which results in an output 1. Okay? As we can see, the OR gate produces a logic 1 whenever one or more inputs is equal to 1. Only the combination 0 or 0 produces a logic 0 at the output. Okay? It's very easy, it's very simple. Now let's continue with another exercise. This time, we have a logical AND operation involving two input variables. As we can see, the logical expression is A times B. And below, we have its equivalent logic circuit implemented with an AND gate. Pause the video and try to solve this exercise by yourself. As always, the first step is to identify the number of input variables. In this expression, we have two input variables, A and B. Therefore, our truth table must contain 4 input combinations. As we already learned, column A changes its value every 2 rows because it has a weight 2 to the power of 1, okay? B is the least significant bit, so it changes its value every row, 0, 1, 0, 1. And now we can determine the output values of this logical function. Before doing that, let's briefly recall the behavior of the AND operation. In Boolean algebra, the AND operation is represented by the multiplication symbol. However, this is not an arithmetic multiplication. Instead, the output becomes 1 only when all inputs are equal to 1. Any combination containing at least one 0 results in an output 0, okay? Let's analyze each row. For row 0, we have A equals 0 and B equals 0. So we have the combination 0 and 0, which results in an output 0. For the row 1, A equals 0 and B equals 1. We have the combination 0 and 1, which results in an output 0. For the row 2, A equals 1 and B equals 0. So we have the combination 1 and 0. Again, one of its inputs is equal to 0, so the output remains 0. And finally, the row 3. A equals 1 and B equals 1, which means both are equal to 1. Therefore, the output becomes 1. As we can see, the AND gate is more restrictive than the OR gate. The output becomes 1 only when all inputs are equal to 1. For this reason, only the last input combination produces a logic 1 at the output. Good job if you got that right. Let's move on to the next exercise. This time, we have a logical expression contains both an AND operation and a complemented variable. As we can see, the function is represented by A plus B complement. And the logic circuit shows that the signal B is first inverted by a NOT gate before entering the OR gate. Pause the video and try to solve this truth table exercise before checking the final result. Okay guys, once again, we begin by identifying the number of input variables. In this case, the expression contains 2 input variables, A and B complement. Therefore, 4 input combinations are required. After completing the input columns, we can focus on the complemented variable. Notice that the expression does not use B directly. Instead, it uses the complement of B. For this reason, before determining the output values, we first need to build the B complement column. Remember that a NOT operation simply inverts the logic level present at the input. Whenever B is equal to 0, B complement becomes 1. And whenever B is equal to 1, B complement becomes 0. In other words, we must invert each logic level of the column B. Applying this rule to each row, we obtain the values shown in the column B, in the B complement column. Note that the intermediate column has been completed. We can evaluate the logical expression. Notice that the OR operation is no longer performed between A and B. Instead, it is performed between A and B complement, okay? Therefore, for each row, we simply analyze the values of A and B complement and apply the OR operation. Now, let's analyze each row, okay? For the row 0, A equals 0 and B complement equals 1. So we have the combination 0 or 1, which produces a logic 1 at the output. For the row 1, A equals 0 and B complement equals 0. We have the combination 0 or 0, which results in an output 0. For the row 2, we have the combination 1 or 1, so the output is equal to 1. For the last row, we have the combination 1 or 0, which results in an output 1, okay? Good job if you got that right. Let's continue with another exercise. This time, we'll analyze a logical function composed of 2 different logic operations. Here we have A and B. The expression is A times B plus C. And below, we can see its equivalent logic circuit. Notice that the AND gate is evaluated first, and its output is then connected to an OR gate. Pause the video and try to solve this truth table exercise before checking the final result. As always, let's identify the number of input variables. In this logical function, we have 3 input variables. Since the function contains 3 input variables, the truth table must contain 8 rows, 8 input combinations. Now, let's begin filling the input columns. Input A is the most significant bit because it has a weight 2 to the power of 2, 4 zeros followed by 4 ones. Next, we complete the column B. Since B occupies the second position, its value changes every 2 rows. As a result, we obtain the sequence 0, 0, 1, 1, 0, 0, 1, 1. And finally, we complete the column C. C is the least significant bit. Its values alternates every row. 0, 1, 0, 1, 0, 1. Okay? Now, before I start filling the output column row by row, let's take a moment to analyze the logic circuit. Sometimes, a careful observation of the circuit allows us to identify important patterns before performing any detailed evaluation, and recognizing these patterns can significantly simplify the analysis of a truth table. Let's begin by looking at the input C. Notice that C is connected directly to an OR gate. And remember an important property of the OR operation. Whenever at least one of its input is equal to 1, the output becomes 1. Therefore, every row where C is equal to 1 will automatically produce a logic 1 at the output, regardless of the values applied to inputs A and B. So we can immediately fill all these rows with the logic 1. Okay? And we can prove this using logic values at the circuit. For example, if C is equal to 1, no matter what A and B are, the output always 1. Okay, now let's analyze the remaining rows. As we learned when studying the AND operation, its output becomes 1 only when all inputs are equal to 1. This means that whenever A and B are equal to 1, the output of the AND gate will also be 1. And the row where A and B are both equal to 1 is the row 6. This means in this input combination, the output of the AND gate will produce an output 1. So a logic 1 will be performed by the OR gate, which will produce an output 1. So we can fill the row 1 with logic 1, okay? And finally, for all remaining rows, C is equal to 0, and the AND gate output is also 0. Since both inputs of the OR gate are equal to 0, the final output must be 0, okay? Notice that we are able to determine the entire output column simply by analyzing the behavior of the logic gates without evaluating every row individually. This is one of the advantages of understanding how logic gates operate. The easier it becomes to recognize patterns and analyze more complex logical functions. So, good job if you got that right. Let's continue with another exercise. Now we'll analyze a logical function composed of an OR gate followed by an AND gate. The logical expression is represented by A plus B grouped inside the parentheses, all these being multiplied by C. And here we can see its equivalent logic circuit. Okay? Pause the video and try to solve this exercise by yourself. Okay guys, if you're ready to try it, let's solve it together. Remember, the first step is always to identify the number of input variables. In this expression, we have 3 input variables, which means our truth table must contain 8 rows, 8 possible input combinations. The column A is the most significant bit. Its value changes every 4 rows. As a result, we obtain 4 zeros followed by 4 ones. The column B has a weight 2 to the power of 1, so its value changes every 2 rows. Column C is the least significant bit, so its value changes every row. Alright, let's analyze the behavior of the logical function instead of evaluating each row individually. Let's first observe the logic circuit and look for patterns. Very often, understanding how logic gates interact allows us to determine several output values immediately, and this can significantly simplify the construction of a truth table. And now, before evaluating row by row, as we did before, let's analyze the behavior of the logic circuit. Again, let's start looking at input C. And remember an important property of the AND operation. Whenever one of its inputs is equal to 0, the output must also be 0. Therefore, every row where C is equal to 0 will automatically produce a logic 0 at the output, regardless of the values of A and B. So we can immediately complete all these rows with the logic 0. Okay, now let's focus on the rows where C is equal to 1. In this case, the final output depends entirely on the results produced by the OR gate. Recall that an OR gate produces a logic 1 if at least one of its input is equal to 1. Therefore, whenever A is 1, B is 1, or both are equal to 1, the OR gate output becomes 1. And the remaining rows that we can identify is row 3, row 5, and row 7. In these rows, C is equal to 1, which means for the row 3, 5, and 7, we'll have the final combination 1 and 1, which will produce the output 1, so we can fill these rows with the logic 1. Finally, let's analyze the remaining row. C is equal to 1. However, A and B are equal to 0. As a result, the OR gate produces a logic 0 at the output, and this 0 is then applied to the AND gate. And because an AND gate requires all inputs be equal to 1, the final output remains 0. Okay? Notice that we completed the entire output column by identifying only two simple patterns. First, every row where C is equal to 0 automatically produced a 0 at the output. Then for rows where C was equal to 1, we only needed to analyze the behavior of the OR gate. This type of reasoning becomes increasingly useful as logical expressions and circuits become more complex. Now let's move on to the next exercise. This time, we'll analyze a logical function implemented with a 4-input AND gate. The logical expression is A times B times C times D, and we can see its equivalent logic circuit. Pause the video and try to solve this truth table exercise before checking the final result. Okay, as always, the first step is to identify the number of input variables. Here we have 4 input variables, A, B, and C. Since the function contains 4 input variables, the truth table must contain 16 input combinations. Now, let's begin filling the input columns. The column C has a weight 2 to the power of 3, which means its value changes every 8 rows. Therefore, we obtain 8 zeros followed by 8 ones. Next, we complete the column B. B has a weight 2 to the power of 2. For this reason, its value changes every 4 rows. Column C has a weight 2 to the power of 1, which means its value alternates every 2 rows. Okay, 0, 0, 1, 1, 0, 0, 1, 1, and so on. And finally, the input D. D is the least significant bit. It has a weight 2 to the power of 0, which means its value changes every row. Okay, now that all input combinations have been completed, let's analyze the behavior of the logical function. Before evaluating the rows individually, let's first observe the logic circuit. Sometimes, a single property of the logic gate is enough to determine almost the entire output column. Notice that all 4 inputs are connected directly to an AND gate. And remember the fundamental behavior of the AND operation. An AND gate produces an output 1 only when all inputs are equal to 1. If at least one input is equal to 0, the output must be 0. Now let's observe the input combinations. Notice that every row except the last one contains at least one input equal to 0. Therefore, all these rows automatically produce a logic 0 at the output. Okay, so we can immediately complete all these rows with a logic 0. Only one combination remains. In the last row, A, B, C, and D are all equal to 1. This is the only row where the AND gate condition is fully satisfied. Therefore, the output becomes 1. Okay? Notice that we completed the entire output column simply by understanding the behavior of the AND gate. Only one combination satisfies the condition required to produce a logic 1. All remaining combinations contains at least one 0 and therefore produces a logic 0. Okay? Okay guys, at this point, I'd like you pause the video and analyze the logic circuit by yourself. Take a moment to observe the relationship between the logic gates and try to identify the pattern that defines the output values. Once you have your prediction, resume the video and compare it with the solution, okay? Let's analyze the circuit together. Notice that this function is composed of 2 AND gates whose outputs are connected to an OR gate, okay? The first AND gate becomes active only when both A and B are equal to 1. Similarly, the second AND gate becomes active only when both C and D are equal to 1. And because both intermediate signals are connected to an OR gate, the final output becomes 1 whenever at least one of these AND gates produces a logic 1, okay? Therefore, every row where A and B are simultaneously equal to 1, the output becomes 1. okay? Likewise, every row where C and D are simultaneously equal to 1, so we have row 6, row 10, and row 14. And where A and B are equal to 1 simultaneously happens to row 11, row 12, row 13, and row 14, okay? Let's test some rows using logical values at the circuit. For example, let's test row 2. Okay, here we have A equal to 0 and B equal to 0. C equal to 1 and D equal to 1. So the combination 0 and 0 produces an output 0. And the combination 1 and 1 produces a logic 1 at the output. So the final output will be 1 because the combination is 0 or 1, which results in an output 1, okay? Let's test another row. For example, the row 12. So we have these input combinations: 1 to the variable A, 1 to the variable B, and 0 to the variable C, and 1 to the variable D. So the combination 1 and 1 results in an output 1, and the combination 0 and 1 results in an output 0. Again, one of the inputs of the OR gate is 1, so the output remains 1, okay? It's very simple. And all remaining combinations produces a logic 0 at the output because neither AND gate generates a logic 1. As a result, both inputs of the OR gate remain equal to 0. For example, let's test some rows. Let's test the input combination of the row 1, okay, which the output is 0. 0 to the input A, 0 to the input B, 1 to the input C, and 0 to the input D. The combination 0 and 0 results in an output 0, and the combination 1 and 0 results in an output 0. So the final combination is 0 or 0, which gives us the output 0, okay? Which means for all remaining rows, the output of the AND gates will always be 0, okay? It's very simple, it's very easy. Okay, at this point, let's just solve this exercise. Pause the video and try to solve it by yourself. At this point, the input columns have already been completed. Since we have worked through several truth tables, we'll focus our attention to the output column and analyze the behavior of the logical function. Rather than evaluating every row individually, let's look for patterns that can simplify the process. Let's begin by observing the logical expression A negated times B plus C. We can say a complement, okay? Notice that the final gate of the circuit is an OR gate. This immediately reveals an important pattern. Whenever C is equal to 1, the output becomes 1, regardless of the values produced by the AND gate. Therefore, all rows where C is equal to 1 can be filled immediately. As a result, rows 1, 3, 5, and 7 will all produce an output equal to 1. With a single observation, we have already completed half of the output column. Now let's focus only on the rows where C is equal to 0. When C is equal to 0, final OR gate can no longer force the output to logic 1. In these rows, where C is equal to 0, final result depends entirely on the output of the AND gate. Therefore, we only need to analyze the expression A complement times B. Notice that the input A is complemented before entering the AND gate. This means whenever A is equal to 1, its complement becomes 0, okay, before entering the AND gate. And remember, in this case, the input C must be 0. Any combination AND with 0 results in an output 0, okay? Therefore, rows 0, 4, and 6 can be completed immediately with 0. In the remaining row, we have the combination 0 to the variable A, 1 to the variable B, and 0 to the variable C. In this case, 0 becomes 1, and B equals 1. So we have the combination 1 and 1, which results in an output 1. The input C is equal to 0, but one of the inputs of the OR gate is equal to 1, which results in an output 1, okay? So we can complete the remaining row, okay? It's very easy, it's very simple. Good job if you got that right. The output column is now complete. Notice that we did not need to evaluate every row individually. Instead, we identify the patterns directly from the logical expression and from the behavior of the AND gates. So, good job if you got that right. Now let's analyze the behavior of this logical function. Identifying the number of input variables, the truth table will contain 16 rows, okay? Pause the video and try to identify the behavior of this logical function by yourself, and try to complete the output column. Let's begin by observing the final gate of the circuit. We can see that the last gate is an AND gate, and we already know an important property of the AND operation. The output will be 1 only when all inputs are equal to 1. This means that if any input of the final AND gate becomes logic 0, the output will also be logic 0. Now let's look at the first level of the circuit. We have two OR gates. The first OR gate receives inputs A and B, and the second OR gate receives the inputs C and D. We also know an important property of the OR operation. An OR gate produces an output 0 only when all inputs are equal to 0. Okay? This observation immediately reveals an important pattern. Whenever both A and B are equal to 0, the first OR gate produces logic 0. And whenever both C and D are equal to 0, the second OR gate produces logic 0. In either situations, one of the inputs of the AND gate receives a logic 0. And whenever AND gate receives a logic 0 at one of its inputs, must also be logic 0, okay? Therefore, all rows that satisfy these conditions can immediately be filled with logic 0 at the output column. Let's verify this with a few examples. Consider row 0, okay? A and B are both equal to 0, and C and D are both equal to 0. Therefore, the first OR gate produces an output 0. Since one input of the final AND gate is already 0, the final output must also be 0. Okay? Let's verify row 12, where A equals 1, B equals 1, C equals 0, and D equals 0. The combination 1 or 1 results in an output 1. And the combination 0 or 0 results in an output 0. Again, at least one input of the AND gate is equal to 0, which results in an output 0, okay? Now, let's analyze the remaining input combinations. If a row was not marked as logic 0 in the previous step, this means that A and B are not simultaneously equal to 0. As a result, the first OR gate produces logic 1. Likewise, C and D are not simultaneously equal to 0. Therefore, the second OR gate also produces logic 1. At this point, both inputs of the AND gate are equal to logic 1. The final operation, therefore, becomes 1 and 1, which means that all remaining rows receive logic 1 at the output column. The output column is now complete. In this lesson, we solved the truth table exercises involving different types of logical expressions and logical circuits. We started with simple examples and gradually moved to more complex circuits containing multiple gates and complemented inputs. Throughout these exercises, we discovered something more important. Building a truth table is not just about evaluating row by row. As your understanding of logic gates improves, you begin to recognize patterns, and these patterns allow you to determine many output values much faster. We also saw that understanding the behavior of each logic gate is essential. When you truly understand how AND, OR, NOT, NAND, NOR, SHOR, XNOR gates operate, the analysis of a logic function becomes much more intuitive. And this is exactly why truth tables are such an important topic in digital systems. They provide a complete description of a logic function, every possible input combination and the corresponding output reduced by the circuit. But truth tables are much more than an isolated concept. They are the foundation for several advanced topics that we will study later. Topics such as canonical forms, kernel maps, logic function simplification, and digital circuit design. So if there's one key idea I would like you to remember from this lesson, it's this. Do not focus only on filling the table. Focus on understanding why each output value is produced. Because once you understand the logic behind the table, everything that comes next becomes significantly easier. In the next lesson, we'll begin studying canonical forms. And there, you will discover how a truth table can be transformed into a Boolean expression. Thank you for watching, and I'll see you in the next lesson.